Hello, good day. I'm Engineer Ernesto C. Prudenciado Jr., and I'm going to discuss today deflection using energy methods. Uh, Energy methods came from our conservation of energy principle in physics that is said to be that external energy is equals to the internal energy, meaning if we have a force applied to the system or to the body, it will just be converted into the summation of all the internal energy. Okay, so in mathematical expression, it is UE equals UI, or the work done external equals to the work done internal. Okay, so external work force, if you can see in the left side, uh, there is a rod connected to the fixed support with the length of L and a cross section of A will be subjected to a force F downward. Okay, so take a look. So force F is pulling it down and have an elongation with the amount of dx. Okay, so of course there is a work there. So the equation is the differential of external work is equals to the force times dx, the distance traveled or the elongation. Okay, so the total work that has been done in the system is equals to, let's integrate the first equation here. That would be UE equals the integral of f dx from 0 to x. So that is the equation if our force is applied consistently to the system. Okay? So what if our force is gradually applied? So we can do it in a graph. Our force will be gradually applied from 0 to the final position P and delta. Okay, so we can have this expression F is equals to P over delta times X, or we can have it by similar triangle F over X equals to P over delta. Okay, so this F will be substituted now by this expression at the top. So this will be equal to the integral of P over delta times X dx, limit from 0 to X. Okay, so we can factor out P over delta. So, and what remains is the integral of X dx. So let's integrate that X squared over 2. Okay, but we know that X now is equals to delta for the final position. So X will be substituted by delta, and the final expression is 1/2 P times delta. This is our equation 1. So this is if the force is applied gradually to the system. How about external work moment? Okay, so essentially it's just the same. It's just that the force here is a rotation, and a distance made by the force is d theta. Okay, with the force M applied. And essentially, the equation is just the differential of external force is equals to md theta. So it is almost the same, no? It's just that f dx here, and this is md theta. Okay, so again, the total work in the system is equals to the integral of md theta from 0 to x. But if the force is gradually applied, we can have also this expression 1/2 m theta, and that would be our equation 2. Okay, so those are the external work applied on the system. As I recall, so external equals internal force. So the internal energy that is being developed because of the external forces, so that we call that as strain energy or internal force. So this time around, we will call that strain energy. So we will solve the strain energy using axial force. So take a look in the figure. So again, there is a rod of the length L and a cross section A. elongate in the amount of delta by a force N. Okay, so in Hooke's law, so recall Hooke's law, that would be equal to the stress is equals to the strain times the modulus of elasticity. Okay, and also stress is equals to N over A. So N is the force over area. And also, we all know that strain is equals to the elongation over the original length, L. Okay? Manipulating the equation, we can solve for the delta equals to NL over AE. Okay? Substituting to the UE, we get, okay, recall to the UE, no? It is 1/2 P delta. Okay? So we have delta in terms of force times distance, or force L over AE. So we can say that N squared L over 2 AE. Okay, 2 here is the 1/2, and the N here is the P times the N above, so N squared L over 2 AE. So this will be our equation 3. So for the strain energy in bending, take a look at this picture. We have a beam and concentrated load P applied at the center with a uniformly distributed W. Okay, we will get the differential strip here, dx. It is measured x from the left support. Okay, so let's take the differential strip, okay, and subjected to a moment m, or subjected to bending. So it will cause the rotation of the theta, okay, as we discussed. So again, the formula or the equation would be the differential of internal work or the strain energy is equals to m d theta. So if the m is gradually applied, we can say that the differential of ui equals to 1/2 m d theta from equation 2, right? So again, integrating that so that we can have the total energy. So we have 1/2 m d theta, but we all know d theta is equals to MEI times dx. It is from the previous lesson. So we can now solve for the total internal force by bending, m squared over 2I dx, limit from 0 to L. So this will be our equation 4. So for the application of what we have learned in the work and energy, let's have an example, number 1. So if we have a beam, a cantilever beam connected with a fixed support at the left, subjected to a concentrated load P with the length is equals to L. Okay? So we all know that if this beam will be subjected to a concentrated load, there will be a deflection. The maximum deflection is at this point, at the right side. Okay, at the rightmost side of the beam. Let's consider a section from our beam. Okay, so let's take the x from the rightmost part. Okay, so this is P, and let's solve for m. Okay, so m in terms of x will be negative px. Negative because it is clockwise. Okay, but you can take also positive, no, as long as you get the m. Okay, so substituting this to our equation, internal energy is equals to integral of m squared over 2ei, limit from 0 to L dx, is equals to, let's just substitute negative px because this is our m. Okay, let's square that over 2ei dx. Factoring p squared over 2ei, what we get is ui equals 1 over 6 p squared L cubed over ei. We all know from our previous equation that ue is equals to ui, or the external force is equals to the internal force. We have 1/2 p delta equals 1 over 6 p squared L cubed over ei. So the deflection at the rightmost part of the beam is equals to PL cube over 3 EI. So this is our final answer. So for example number 2, look at this beam, okay, and subjected to a concentrated load P. So this is not in the center. Let's just put the load P arbitrarily along with the L. So the first section is A and the second section to the right is B. Okay, so there is a point here, A, the hinge support, and B is concurrent to force P, and C is on the roller support. So summation of moments about A or C, we can take the reaction of PB over L at A, and in reaction C is PA over L. If we take a section A here and solve for the moment, summation of moments about this point, so we can have MA equals PB times XA over L. Okay, let's substitute that to our equation. M squared integral of M squared over 2EI dx with limit 0 to A. So we have P, since we will square the M, so P squared B squared times XA squared over 2 L squared EI dx. Okay, so factoring out PB 2 L squared EI because this is constant, and let's integrate X squared dx. So what we have is X cubed over 3 times 2 in the denominator. We have, that's why we have 6 here. X now will be substituted by A, so this one is P squared A cubed B squared over 6L squared EI. Okay, so the same also if we take the section B, no, from the right support. So we take the X from the right support. So again, we will take the moment. That would be, okay, PA X times the moment arm XB over L. Okay, so we can also get the energy of section B. So again, this is the formula M squared over 2EI. So substituting that, so this becomes P squared A squared XB squared over 2L squared over EI times dx. So factoring out P A 2L squared EI and integrate XB squared, so that would be X cubed over 3. So 3 denominator times 2, this will be 6. That's why we have 6 here. So substituting B to the X cube, so there will be B cubed. So P squared A squared B cubed over 6L squared EI. Okay? The energy total is equals to the summation of two sections, the energy of two sections, UA plus UB. So U total is equals to, this is UA, this is UB. So what we have done here is just factor out P squared because this is common, and A squared here. So there will be A left here and B squared also. And the same with the denominator, let's factor out all. Then here we factor out P squared, A squared, and B squared. So we have B here. We left A and we left B here. So this is now the expression P squared, A squared, B squared over 6L squared EI times A plus B. But take notice this expression, this is equal to what? That is equal to L. So we can cancel out L here and 1L here. So what we have left is P squared, A squared, B squared over 6L EI. So the energy total, this one, will be equated to the external energy which is 1/2 P delta. So we can cancel out P here. So we have 1 P left in the equation. So we can solve for delta equals P A squared B squared over 3 L EI. So this will now be our deflection of our simply supported beam subjected to a concentrated load. So how about if the P is at the center, you will just replace A squared B squared into L over 2 squared. So that would be easy. Okay, so thank you.